Rancho Palos Verdes is dealing with more land movement.
So a large section of the bluffs actually gave way over the weekend, impacting several.
In early autumn, a section of the coastal bluff along Rancho Palos Verdes gave way without warning. The collapsed stretch, estimated between 300 and 400 feet in length, or roughly 90 to 120 meters, slipped toward the Pacific Ocean, dislodging backyards, irrigation systems, and fragments of concrete retaining walls. The scene became a localized emblem of geological tension, visible evidence of how slow-moving forces in the Earth's crust intersect with rapid surface processes. Yet, beyond the immediate destruction lies a deeper question of mechanism. What is actually happening along California's rising coast? Is this the expression of long-term tectonic uplift, local gravitational failure, or a combination of both operating on different timescales? From a geological perspective, the event in Rancho Palos Verdes cannot be isolated from the larger tectonic framework that defines coastal California. The state's western edge is part of the Pacific, North American plate boundary, where the Pacific plate moves northwest relative to the North American plate at a rate of about 2 inches or 5 centimeters per year. While this motion is primarily horizontal, the configuration of faults, bends, and compressional zones occasionally converts lateral slip into vertical uplift. Over millions of years, this differential movement has produced the transverse ranges, the peninsula ranges, and the elevated coastal plateaus like Palos Verdes. The peninsula itself represents a block of crust that was once part of the continental shelf and has been gradually tilted and lifted since the late Miocene epoch, roughly 15 million years ago. This uplift is not uniform. It manifests as broad folding and faulting, generating an irregular pattern of rising terraces and steep cliffs. Geophysical surveys have mapped an anticline structure running parallel to the shoreline beneath Palos Verdes. The anticline, essentially a bulging fold in layered rock, formed under compressional stress as regional forces along the San Andreas system reoriented. The crust beneath this area accommodates strain through subtle but persistent deformation, elevating older marine sediments far above their original depositional level. The exposed rocks include alternating beds of sandstone, siltstone, and volcanic tuff, deposited in shallow marine environments before being tilted and uplifted. Evidence for this long-term rise is preserved in the marine terraces that step upward from the modern shoreline. Each terrace represents a former wave-cut platform formed at sea level before being lifted by tectonic forces and stranded above the present ocean. On the Palos Verdes Peninsula, at least 13 distinct terraces have been identified, some elevated to nearly 1,200 feet, or about 365 meters above current sea level. Using radiometric dating and fossil assemblages, geologists estimate that the average uplift rate for this segment of the coast has been approximately 2 to 3 inches, or 5 to 7 centimeters per century, over the Quaternary period. Though imperceptible on a human timescale, these rates are considered rapid in geological terms, enough to remodel entire coastal landscapes over millions of years. However, what occurred in Rancho Palos Verdes was not the result of active tectonic uplift on a short timescale. The bluff collapse was gravitational, a mass-wasting process driven by material instability within the slope. Beneath the surface veneer of soil and weathered rock lies a stratified sequence of sedimentary formations, including weak clay layers derived from altered volcanic ash. These layers, often bentonitic in composition, exhibit high plasticity and low shear strength when saturated. During prolonged rainfall, groundwater percolates through fractures and accumulates above less permeable strata, increasing pore pressure. The rise in pore pressure effectively reduces friction along these weak planes, allowing overlying material to slide. When the balance between gravitational force and internal cohesion is exceeded, a failure occurs. In this case, the failure likely propagated along one of these ancient bedding planes, releasing a block of the bluff that slipped toward the ocean. The pattern of collapse, curved, concave and localized, suggests a rotational slump rather than a deep-seated fault rupture. The absence of seismic signals preceding the event supports this interpretation. No regional tremor was recorded coinciding with the failure. Moreover, satellite interferometry data collected before and after the incident show surface displacement consistent with downslope motion, not uplift. Still, the fact that the Palos Verdes Peninsula is geologically active invites confusion between uplift and sliding. On a long temporal scale, the region is indeed rising due to crustal compression. But this rise is punctuated by local subsidence events when gravitational forces overcome internal resistance. It is an interplay between construction and destruction, where tectonic elevation and erosional collapse alternate through cycles of stress accumulation and release. Coastal uplift slowly raises the land, while gravity and erosion relentlessly attempt to return it to equilibrium. Beyond Palos Verdes, the same principles apply along much of California's coast. From Point Conception to Monterey Bay, numerous marine terraces mark past high stands of sea level, followed by tectonic uplift. In the Big Sur region, vertical displacement rates derived from cosmogenic nuclide dating suggest uplift on the order of 1 millimeter per year, approximately 0.04 of an inch. In Northern California, near Cape Mendocino, rates exceed 4 millimeters, roughly 1/6 of an inch per year, owing to the subduction of the Gorda Plate beneath the North American Plate. In contrast, the Southern California coast experiences mixed effects, with some segments like San Diego and Los Angeles showing slow uplift rates of less than 1 millimeter per year, roughly 0.04 of an inch, which is comparable to or slower than the current rate of sea level rise. The overall impression of a rising coast therefore depends heavily on spatial and temporal scales. While geological evidence clearly demonstrates net uplift over millions of years, present-day vertical motion is minimal. What residents perceive as sudden changes, such as bluff collapses, reflect localized slope instability rather than broad tectonic elevation. The mechanisms driving these events are primarily hydrogeological and gravitational, with tectonic context serving as the long-term framework that shapes the terrain in which such slides occur. Another important consideration is the role of lithology and weathering. The Palos Verdes Peninsula is composed of alternating hard and soft layers, sandstone, shale and volcanic tuff, each responding differently to stress and moisture. The softer, clay-rich strata act as slip planes when lubricated by infiltrating water. Recurrent wet seasons, combined with the removal of vegetation and artificial loading from structures, accelerate these processes. Over time, the same mechanisms responsible for slow crustal uplift also contribute indirectly to slope failure, as faulting and folding produce steep relief that gravity continuously seeks to level. The Palos Verdes fault zone, which runs offshore, is an additional factor. This fault is classified as a right lateral strike-slip system, meaning the crustal blocks move horizontally past each other. While such faults are primarily lateral, they often include a minor vertical component known as oblique slip. Geological mapping indicates that in segments near the peninsula, this fault has produced modest vertical displacements, raising one side slightly relative to the other. However, these movements occur episodically during earthly years and are measured in inches rather than feet. Over long periods, such incremental uplifts accumulate, but they do not produce the kind of sudden vertical displacement that could explain a cliff collapse. Furthermore, the stress field around strike-slip faults can generate secondary features like small reverse faults and folds, which contribute to the uplift of coastal blocks. In the Palos Verdes area, these secondary structures have gradually elevated the peninsula relative to the Los Angeles basin. Yet these tectonic mechanisms operate over thousands to millions of years, contrasting sharply with the instantaneous nature of a landslide. The key distinction lies in process duration and energy source. Tectonic uplift stems from deep crustal forces acting over geologic time, while bluff collapses arise from surface instabilities acting under gravity's influence on much shorter timescales. What connects these phenomena is their cumulative effect on landscape evolution. The same tectonic compression that raised the Palos Verdes Peninsula also created the steep topography prone to slope failure. Without uplift, there would be no cliff to collapse. Without erosion and gravity, the uplifted land would persist indefinitely. The coast's apparent rise and its periodic collapses are therefore two sides of a single geodynamic equation. As investigations continue in Rancho Palos Verdes, engineers and geologists use tools such as LiDAR mapping, ground-based radar interferometry, and borehole piezometers to monitor minute ground movements. These instruments reveal that the rate of movement in certain sectors of the peninsula fluctuates seasonally, correlating with rainfall and groundwater variations. During dry periods, the ground remains largely stable. During wet winters, slope motion accelerates. The data indicate ongoing creep, downhill movement measured in millimeters per month, which underscores the role of hydrological loading rather than tectonic forcing. Understanding this interplay between slow uplift and rapid failure requires integrating structural geology, geomorphology, and hydrogeology. The Palos Verdes case exemplifies how multiple natural processes can act simultaneously, producing outcomes that superficially appear contradictory. While one part of the coast is technically rising, another is collapsing. The uplift is real, but imperceptibly slow. The collapse is dramatic, but locally contained. Together, they shape a coastline in perpetual adjustment, balancing tectonic construction with gravitational destruction. Along California's coast, every contour of the land speaks of slow but relentless deformation. The gradual rise observed in certain areas, including Rancho Palos Verdes, is not an anomaly, but a manifestation of complex tectonic forces operating along the Pacific North American plate boundary. Here, stress is not confined to a single fault, but spread across a network of structures where compressional and strike-slip motions interact. The Palos Verdes fault zone, together with the Newport-Inglewood system and several smaller faults, partitions this motion and converts a portion of lateral shear into vertical displacement. Over centuries, this interplay builds a crustal block that ascends imperceptibly, a process measured in millimeters each year, barely a fraction of an inch, yet monumental in geological terms. High-resolution GPS and INSAR monitoring confirm that certain coastal sectors of the Palos Verdes block are moving upward at rates approaching 2 millimeters per year, or about 0.08 of an inch. Though seemingly negligible, These increments accumulate over millennia, forming the marine terraces that line the Southern California coastline. Each terrace represents an ancient shoreline, a marker of past uplift events. These step-like formations record the rhythm of the Earth's crust as it flexes, rises and pauses, a living record of deformation written in stone. The mechanism driving this uplift lies within what geologists describe as a restraining bend, an irregular curve in a strike-slip fault that forces the crust to compress. When horizontal motion is impeded by such a bend, the rock layers buckle upward, producing folding and fault propagation structures that gradually elevate the surface. In the Palos Verdes region, this bending effect is subtle but persistent, and over hundreds of thousands of years, it has sculpted a ridge that continues to rise even as its edges crumble under the stress of gravity and waves. While tectonics construct the landscape, it simultaneously sows the seeds of instability. Each pulse of uplift fractures the bedrock and alters drainage pathways, allowing water to infiltrate deep into the slope. Over time, chemical weathering and mechanical stress weaken these fracture zones. When pore pressure rises, especially after heavy rainfall, the weakened layers lose cohesion, and gravity completes the work that tectonics began. The result is a landslide, often sudden but long prepared by unseen processes. The recent collapse of the 300 to 400-foot section of bluffs at Rancho Palos Verdes is part of this cycle. Uplifted terrain adjusting under its own weight, gravity restoring equilibrium one failure at a time. Regional deformation patterns also reveal that uplift rarely acts in isolation. The California margin behaves like a flexing beam, one end rising as another subsides. The same forces that raise the Palos Verdes Peninsula help depress the Los Angeles basin, producing a dynamic equilibrium that balances crustal motion. This flexural response, driven by compressional stress and the varying density of underlying rock, explains why certain parts of the coast appear to rise, while others sink at comparable rates. It is not the coast itself that rises independently, but rather a series of interconnected blocks shifting within a deforming lithosphere. The deeper crustal processes beneath this region amplify the complexity. Numerical models show that deformation is concentrated near fault intersections, where compressional stress is highest. In these zones, the rock behaves plastically, folding instead of fracturing, and transmits stress to the surface as slow, elastic uplift. Unlike abrupt earthquake movements, this uplift is steady, elastic, and largely aseismic, driven by strain accumulation that never fully releases in a single rupture. Each episode adds a minuscule increment of vertical motion, contributing to the broader rise of the coast. Over the last million years, repeated cycles of such uplift have created stair-step terraces, visible reminders that the coast is anything but static. Cosmogenic nuclide dating confirms that terrace surfaces rise in sync with fault activity, suggesting that the current uplift pattern mirrors the long-term tectonic rhythm of Southern California. Some terraces now sit more than 100 meters, or 330 feet, above the modern shoreline, a silent measure of crustal persistence over time. Still, tectonics alone cannot explain all vertical adjustments. Magmatic activity from the Miocene epoch left behind dense igneous intrusions beneath the region. These hardened structures act as mechanical anchors, redistributing stress toward adjacent sedimentary layers. When these weaker rocks deform, they uplift unevenly, amplifying the topographic contrasts visible along the coast today. Such lithologic contrasts are fundamental to understanding why certain slopes, like those in Rancho Palos Verdes, are more prone to fracturing and collapse than others nearby. Crustal motion, uplift, flexure and gravity together create a feedback system that continuously reshapes the California coast. The apparent rise of the shoreline is not a simple vertical movement, but a complex response to horizontal compression, crustal bending, and mass redistribution. What appears to be coastal rise is often a composite of uplifted rock, subsiding basins, and retreating cliffs. Each process operates on its own timescale, the crust rising over thousands of years, the waves eroding cliffs over decades, and landslides occurring within moments. As the 21st century progresses, climate variables add another layer of influence. Intense rainfall events, fluctuating groundwater levels, and ongoing sea level rise interact with pre-existing tectonic stress to destabilize slopes. Even if the crust continues its slow ascent, the competing process of erosion may offset or obscure that gain. The balance between uplift and retreat determines the coastline's future profile. In places like Palos Verdes, the struggle between tectonic construction and oceanic destruction is visibly active, reminding us that Earth's surface is never still, only shifting at scales beyond daily perception. Ultimately, the so-called rising coast of California reflects a living system of geological adaptation. Tectonic compression lifts the land, gravity resists that uplift, and erosion continually redraws the line between land and sea. Every terrace, landslide, and marine platform represents a chapter in an ongoing story of crustal transformation. What collapsed in Rancho Palos Verdes was not merely a bluff, but a record of Earth's internal dynamics playing out in slow motion. And as we study these movements through precise instrumentation and patient observation, we glimpse the long game of planetary architecture, an equilibrium that never fully settles but endlessly evolves. California's coastline, far from being a static frontier, is the surface trace of deep geologic conversations that have been unfolding for millions of years. If you found this exploration insightful, make sure to like, share and subscribe, and tap that hype icon to help this video reach a wider audience, because understanding our planet's movements is the first step toward living in harmony with them.